So in this introduction, we're going to look a little bit at some of the basic parts of the urinary system and how those basic parts make urine. And so these are some of the prefixes, root word suffixes that you'll see throughout this PowerPoint. A couple big ones you're going to see throughout here. You're going to anything that has "rene" in it, anything that has to do with the kidney. You're going to see some words that have "eme" or "heme" in it that has to do with blood. Anything that has UR in it has something to do with urine. Those are going to be some of the big ones you'll see in here. Now, the basic setup of the urinary system, we do have two kidneys. My little note, the right kidney, right side of your body, does sit a little bit lower than the left kidney. It's not a huge difference, but if you notice the right one sits a little bit lower, main reason for it is you have a big, huge liver that sits right up here on this side of the body. And so that kind of pushes down on your right kidney a little bit. But otherwise you have two kidneys. Connected to each of the kidneys, you have these long tubes called your ureters. The two ureters join together and drain urine into the urinary bladder. And the urinary bladder is just to store urine. And then the urethra is going to transport urine out of the body. Basic parts of the urinary system. Today we're mostly, in this intro, we're mostly going to focus on the kidneys, because that's really, lots of stuff's happening in the kidneys. Most of the other things is just transport or storage of the urine. But kidney is where all that filtration, all of that urine itself is being formed. So some of the functions of the kidney, well, they regulate your total water volume in your body and your total solute concentration. That's also in the water part of your body. Now, kind of a key thing to know, not just in this unit, but in other units, is that wherever solutes are, and that could be salt, that could be sugar, that could be proteins, wherever the solutes are, things that can be found in a fluid, water is always going to want to follow. It's kind of the basic, it's just water follows solutes. It's a good rule, not a bad thing to write down somewhere. Water follows solutes. So it's the same reason why if you just got done eating some really salty popcorn, well, that's a lot of salt, which is a solute. Water needs to follow, which is why you're feeling thirsty. And so our kidneys regulate a lot of our water volume because we can regulate the solute concentrations in different areas. Our kidneys can also regulate our extracellular fluid ion concentrations. This includes sodium, this includes potassium, this includes calcium. These are the ions that are even needed in our nervous system for just electrical conduction. It can help ensure long-term acid-base balance, that if your blood is becoming too acidic, you have too many hydrogen ions, we can secrete some of those into our urine to get rid of them out of our body. It can remove various types of metabolic wastes, it can remove toxins, it can remove drugs. It also has various types of endocrine functions, and the endocrine system has to do with hormones. One is that we do find renin, which is an enzyme, but it works with various types of hormones in the regulation of blood pressure. It also has erythropoietin, which is a hormone that regulates red blood cell production. The word erythropoietin is a hormone that makes, poietin means make, and erythro means red. It's the hormone that helps make red blood cells if you need it. And it can also activate vitamin D if we need absorption of calcium. So our kidneys, everyone's like, urinary system makes urine, but it does more than that. It's one of those, everyone just thinks it just makes urine, but the urinary system is one of the most important systems of them all. It's one of the main reasons why they will not discharge someone from a hospital until they can look to see at their urinary output and look at their urine to see that the kidneys are working properly. Because if the kidneys aren't working properly, it could be a blood pressure issue, it could be a blood volume issue. And I'm like, if your kidneys aren't working, lots of things can go wrong. Now, as I mentioned before, the right kidney does sit down a little bit lower because it's crowded out by the liver. Also sitting on top of each of the kidneys, there is an adrenal gland. And the adrenal gland, although it sits on top of the kidneys, really has nothing to do with the kidneys, but you can see it on there. I'm going to go back to my picture. There's the adrenal gland. It's part of the endocrine system. We also have part of, draining out of the kidneys, we have the ureters. We've got various types of blood vessels that are going in and out. We have paralymphatic vessels that are going in there. And we also have various types of nerves that are going in and exiting at what's known as the hilum. The hilum is the indent in the kidney. And I'm like, just the fact it looks like that characteristic kidney bean, and I'm like, the hilum is just the indented area of the kidney bean. And so you have lots of things going in, lots of things coming out, all at the kidney. Now, if we're going to look a little bit more at the inside of the kidney, some of the internal anatomy, and you guys can keep this, if you've got this printed, you guys can take a look at this. I'm going to kind of read through this, but with a picture in front of me. So some of the basic parts of your kidney. Once you slice it up, here's an actual picture of the kidney. Here's our book-drawn picture of it. And there's that nice indented region. Lots of things going in and out in the hilum region. But the outer part of the kidney is known as the cortex. Color-wise, it's a little bit lighter. Just like your cerebral cortex is the outer part of your brain, you have a renal cortex. It's the outside of the kidney. Inside of there, the whole kind of this inside area is known as the medulla region, inside of the cortex region. And it's in this medulla region we've got several things. One, all these triangular shaped structures are known as renal pyramids. Just like a pyramid looks like a triangle, so do these a little bit. And they're found inside the kidneys. We also have these little spaces in between all those pyramids called columns. They look nice and tall, like a nice tall column. At the bottom of any of these pyramids, because you're going to have lots of urine getting formed in these pyramids, and that urine is going to get dumped into, if that's a good way to say it. At the bottom, all of the urine that's getting formed inside these pyramids is going to dump into what's known as a minor calyx. Different minor calyxes will form together and join together into what we call a major calyx. You've got minor calyces, major calyces. All the major calyces, lots of urine formed here, is all going to dump into this big middle region known as the renal pelvis. And the renal pelvis is a big funnel-shaped tube that's going to just drain that urine out of the kidneys into the ureters. So we've got kidney getting formed in the pyramids and up in the cortex, drain down to the bottom of the pyramid into the calyx, minor calyx, into the major calyx, into the renal pelvis, and then out of the kidney through the ureter. So kind of basic parts of the inside of the kidney. Now, your blood supply to your kidney. So you have lots of blood supply to your kidney. Now, the main job of the kidney is to filter our blood. They cleanse our blood, they adjust the composition of our blood, and so they have to have a rich blood supply. Your renal arteries, you have a big huge artery that's going into the kidney, delivers about 1/4 of your heart output to your kidneys every minute. That's a lot of blood that's being sent to the kidneys. We want to be filtering it. We want to be able to get rid of stuff out of the blood we want out of the blood and put stuff into the, into the blood that we need to save in the blood. And so we've got lots of blood vessels going in and out of the kidneys. So you have a renal artery that's taking blood in. You have a renal vein that's bringing that filtered blood out. Also, if you notice, we've got lots of veins and arteries that as they start to branch inside the kidney, they're called the same thing, except one's called an artery, one's called a vein. So you've got arteries and veins up in the cortex region. You have arteries and veins that are kind of joining right below those arteries and veins. You have something known as the interlobar artery and vein. And if you notice, pretty much wherever there's a red artery, you're going to have a blue vein right next to it. They run in very similar paths to each other. Now, the kidneys make the urine. That's where urine is formed. However, the whole kidney itself does not make urine. It's inside of the kidneys we have structures called nephrons. These are the structural and functional units that actually make the urine. And so when we talk about kidneys making urine, it's really the fact that there are well more than 1 million of these nephrons in each kidney, and it's these nephrons make the urine. So nephrons make the urine in the kidneys. So yes, when we talk about kidneys produce urine, well, inside of the kidneys, urine is produced. It's the nephrons that are really making the urine. And the nephrons are split up into 2 main parts. There's a renal corpuscle, which I'll talk about first on my next slide, and there's a renal tubule. It looks like a big, huge, long tube. So we're first going to look at the renal corpuscle, the first part of the nephron. And the renal corpuscle, this first part of the nephron, is also divided into two parts. So the renal corpuscle, first part of the nephron, is made up of what's known as the glomerulus and then the glomerular capsule, sometimes also known as the Bowman's capsule. I like it when things have two names. They mean the same thing. Don't care which one you want to remember. But the glomerulus is really kind of the heart of the renal corpuscle. This is where you have that blood filtration happening. The fact that we have blood going in and blood coming out of the kidneys, it has to get filtered, and the filtering is happening inside the renal corpuscle, specifically at the glomerulus. This is your capillaries that is bringing lots of blood supply to the kidneys to get filtered. And it's in that glomerulus where you have all these capillaries. It's highly porous. They call it fenestrated. It's lots of pores, so you have lots of things that can leave the capillaries, lots of things that can leave the blood supply, lots of fluid volume that can leave that blood supply. And it's that porous filtration happening there that allows what's known as filtrate to be formed. Just means it's now been filtered out. My only note, and I'm like, although we have lots of filtrate being formed, lots of stuff can leave your blood and get filtered out in the glomerulus and make filtrate, most of filtrate just gets reabsorbed right back in. And so we're going to make lots of filtrate. Filtrate is not technically urine yet because we're going to modify it. We're going to reabsorb a lot of water back out. We're going to maybe secrete stuff into it. But filtrate just means it's a fluid that we've filtered in the glomerulus. Now, surrounding the glomerulus, because in this structure, this big tuft right here, glomerulus, on the outside part, the glomerulus sits inside of a capsule. It's almost like its own little protective capsule. So it's a little cup-shaped hollow structure that surrounds the glomerulus. That's known as the renal capsule or the Bowman's capsule. Just to look at a different picture, so this huge structure, all of this tube, plus this, is the nephron. This structure right here is that renal corpuscle, the first part of the nephron. And again, it's divided into two parts. The glomerulus, where you have those capillaries for filtering of blood, and you have the capsule on the outside that surrounds the glomerulus. Now, after this blood gets filtered and we make filtrate, it's going to go into that capsule and it's going to go into the next part of the nephron, the renal tubule. So we're going to take that filtrate and it's going to go first into this area right here that's known as the proximal convoluted tubule. Proximal because it's closest to the renal corpuscle. Convoluted because convoluted means pretty much twisty, turny. It's a windy tube, so we call it convoluted. So it's proximal because it's close to that renal corpuscle, convoluted because it's twisty, turny, and it's a tube. That's where it gets its name from. That's the first part of the renal tubule. After this proximal convoluted tubule, it goes into this big, huge loop, which we call the nephron loop, also called the loop of Henle. I'm seeing it more called the nephron loop than the loop of Henle. And then after that nephron loop, we go and we have another convoluted, twisty, turny tubule, and it's called the distal, because it's farthest from the renal corpuscle. Now, the proximal convoluted tubule, this first twisty, turny part right after the renal corpuscle, where you just got done making filtrate. We just filtered all of that blood and filtered a lot out. So we have our filtrate. It's going to go first through the proximal convoluted tubule. Now, the structure of the proximal convoluted tubule kind of shows that there's a lot of stuff going on in just this one twisty, turny tube. One, we do have some cuboidal cells, and they have dense microvilli. We've got all of this microvilli on the top of these cells, and that's there to increase surface area. Just like you have microvilli in your small intestines to increase surface area, you do in that proximal convoluted tubule as well. Main reason we have lots of surface area right there is we have lots of reabsorption and lots of secretion happening. And so we have lots of reabsorption. Again, most, like 99% of all that filtrate, it's going to get reabsorbed right back into your bloodstream and not become urine. And so that surface area lends itself to that. We also have a lot of secretion happening. There's some stuff that's in our blood that we want to get rid of out of the body, whether it's various types of ions, whether it's various types of drugs, and we could secrete various things out of our blood supply into this proximal convoluted tubule. There's also a lot of mitochondria found in there, and the proximal convoluted tubule hangs out in that outer renal cortex, the outer part of the kidney itself, kind of that lighter colored area. Now the nephron loop, that comes all the way down. So it has a descending part of the loop and it has an ascending part. The descending part is attached to the proximal convoluted tubule, and the descending limb is made of a simple squamous epithelium. Again, it's just the same type of tissue you have in your lungs because you want lots of stuff to get out and lots of stuff to go in so that you can have lots of reabsorption happening. The upper ascending limb of the loop, it has both a little thin area and a thick area. Mostly you have cuboidal cells, some you have columnar cells, sometimes you have those thin regions in there. Either way, it's simple tissue. We still have lots of reabsorption and secretion that can happen in there. And the last part of the renal tubule we have is the distal convoluted tubule. So it's farthest from the renal corpuscle, and it's still twisty-turny, still a tube, and there's not as much happening in the distal. Lots of stuff happens in that proximal. So it's still cuboidal cells, not as many microvilli. We don't need as much surface area here. And really what's happening mostly in the convoluted tubule is more secretion than anything else. When the body wants to get rid of something to go into the urine, to get urinated out, it's usually going to happen in the convoluted tubule. More of the reabsorption happens in that proximal convoluted tubule. Now, the distal convoluted tubule is also found out in the cortex region. It's really only this loop of Henle that's found down in the pyramid region of the kidney, down in those little triangular regions. Now, at the end of the tubule, you have what's known as a collecting duct. And the collecting duct receives filtrate from lots of nephrons. And it's really by the time it leaves the collecting duct, there's still some more reabsorption or secretion that can happen here. But by the time it leaves the collecting duct, we no longer call it filtrate and we call it urine. But the collecting duct's going to receive filtrate from lots of nephrons. One nephron does not get its own collecting duct. It's a collecting duct and it collects from lots of nephrons. It collects lots of filtrate from lots of nephrons. And at the bottom part of the collecting duct, it runs through the pyramids, which is why the pyramids kind of have a striped look to it. But at the bottom of the collecting duct, this is where it delivers the urine, it's now urine, into the minor calyces. Let's see if I'm going to go back to a picture of my kidney. And so these pyramids are looking striped is because you have these collecting ducts in there. And the collecting ducts are going to deliver urine to the tip of the pyramid into the minor calyces. And again, it's urine at this point. We're not really going to change anything about the urine once it dumps into those minor calyces. Now, that's the basic setup of the nephron. And I'm like, we'll talk more about reabsorption and secretion and the filtration that happens, but that's the basic setup, the organization of a nephron. And I'm like, that it has a proximal and distal convoluted tubule, that it has a big huge loop, that it has that renal corpuscle where you're going to have filtration happen. Now, there are two looking nephrons. There are cortical nephrons and there are what are known as juxtamedullary nephrons. Most of the nephrons are called cortical nephrons, is because all or majority of it is found up in the cortex. That the proximal convoluted tubule, the distal convoluted tubule, the renal corpuscle, all happens in that outer cortex. The only part that's not in the outer cortex is that loop, that nephron loop that hangs down. And that's what most nephrons are. However, there's still some nephrons that are called juxtamedullary nephrons because they have super, super long nephron loops. So that's the biggest difference. They have really long nephron loops. And the main job of these particular nephrons is making really concentrated urine. Whether it's because you're dehydrated, whether it's because you have to get rid of a lot, I don't know, whether it's drugs or ions or whatever, you have to get rid of a lot of stuff and secrete it out of the body. These nephrons, because of those long nephron loops, are important in producing concentrated urine. Now, just looking at the difference, here's a normal cortical nephron, that you've got that renal corpuscle, proximal, distal convoluted tubule, all happening in this outer cortex region. Only the loop of that nephron loop, or loop of Henle, hangs down into the pyramid. The juxtamedullary nephron still has a renal corpuscle, still has a proximal convoluted tubule, it's still going to have a distal convoluted tubule, but it has this massively long nephron loop. Now, the blood vessels around it are also a little bit different. And I'm like, it's still the same basic setup. It still has the renal corpuscle, still has proximal distal convoluted tubules, still has a nephron loop. It's just the nephron loop is a whole lot longer, and it's going to have a slightly different blood vessel setup. So, blood vessel wise, so there are two capillary beds, so two places where you're going to have filtration or reabsorption or secretion happening in your nephrons. The main first one is in the glomerulus. This is where you're going to have that main blood filtration happening to make our filtrate, to make the urine. We also have peritubular capillaries. These are the blood vessels that are found around the tubes. That's why it's called peritubular. Peri means around, like a perimeter. It's around the tube, so peritubular, and it's a capillary. Now, the juxtamedullary nephron is also associated with what's known as the vasa recta. And I'm like, these are the veins that surround that long nephron loop. So here are the peritubular capillaries, again, blood vessels, go around the tubes. The vasa recta, part of the juxtamedullary nephron. And I'm like, those capillaries are really going to go around that nephron. Again, so we can secrete lots of things into that urine so that we can make that concentrated urine. Now, the glomerulus, its main job is to filter your blood. That's its job. It's specialized for filtration. So we're going to filter blood, and because its main job is to filter, it's structured to maximize the filtration. So it's different than other capillary beds. Most capillary blood beds have very low blood pressure, and I'm like, low blood flow, so that we can just drop off oxygen, pick up carbon dioxide, and we can maximize that. Well, the capillary beds in the nephron are not just to drop off oxygen and pick up carbon dioxide. We need a high blood pressure, and we need to be able to have that high blood pressure to push that blood through those filtration membranes to filter the blood. And so we have a blood vessel going into the glomerulus and a blood vessel coming out. The one that goes in is the afferent. I think A for approaching. It's going in. And then the blood vessel, or the arteriole that comes out, so it's not artery vein, they're both arterioles. The blood vessel coming out is known as the efferent. The only letter different between the two is the first letter, afferent and efferent. Ways to remember which one goes in, which one comes out. Afferent, A for approaching. Efferent, E for exiting. So afferent arteriole goes into the glomerulus, efferent arteriole comes out. Now, we have to have that high blood pressure in there, enough pressure to push the blood through that filtration membrane to make filtrate. And a couple things that help create that high blood pressure. One of the biggest one is that your afferent arteriole is larger or wider than your efferent arteriole. See if I can find a picture that's going to show that well. This one looks good. I'll go back. And I'm like, your afferent arteriole, where blood vessels, or your blood supply is going in, is wider than the efferent arteriole. And just like when you're driving, if you have to go from a 3-lane highway to a 2-lane highway, and I'm like, when you are going from something wider to something narrower, and I'm like, it's usually a traffic jam, there's a higher pressure. It's the same basic idea. You have the same amount of blood that has to flow through here, that has to flow through there. Well, if you narrow the path, that blood that's coming out is going to be under higher pressure. You're shoving that same volume of blood into a narrower passageway. It's going to be under higher pressure in here when you shrink that. That's one of the biggest things that creates this nice high pressure in the glomerulus. Go back. The other is just the arterioles themselves are high resistance vessels. They're not doing anything to slow it down. They don't have a lot of friction that's happening in there to slow the blood vessels down. And I'm like, so that we have nice high blood pressure in there to cause that filtration to happen. Now, the other blood vessels, so we've got blood vessels going in and out. So for filtration, we also have our peritubular capillaries. Again, just their name means they're around the tubes. And the peritubular capillaries also low pressure, also porous, and they're adapted for the absorption of water and solutes. So when we have filtration happening in the glomerulus and filtrate ends up in these peritubular capillaries, again, 99% of that filtrate ends up right back in the blood supply. So you've got a nice, slow, low pressure blood supply right next to the peritubular capillaries to catch all of that reabsorbed filtrate. Now, my note is that these peritubular capillaries come from the efferent arteriole. So you have blood, high, low pressure because of that wide blood vessel. And I'm like, that goes into the glomerulus to get filtrated. And that efferent arteriole that comes out, that is narrower, so that you have a high blood pressure in here, that narrow efferent arteriole is going to split and divide and become the peritubular capillary. So that's where these capillaries come from, is they come from the efferent arteriole, and they're just hanging out on those proximal and distal convoluted tubules out in the cortex region. The other capillary bed that we have is the vasa recta. The vasa recta is associated just with the juxtamedullary nephrons, the ones that have those long loops, those long nephron loops. It also comes from the efferent arterioles, so both of those capillary beds, whether it's the peritubular or the vasa recta, are coming from the efferent. And so you have blood going in, blood coming out, and it's the blood that goes out that becomes the vasa recta. And it's these blood vessels that are there to absorb lots and lots of water out of that filtrate so that you can have a really concentrated urine. Now, as I said, 99% of your filtrate gets reabsorbed, and it does. You make about 180 liters. That's 92-liter bottles. And I'm like, you make that much filtrate every single day, but only about 1.5 liters actually becomes urine. That means the other 178.5, and I'm like, all has to get reabsorbed back into your blood supply. So the kidneys filter a lot of your blood supply. Our kidneys filter your entire blood volume about 60 times a day. That's lots of filtration happening. That's lots of filtrate getting made. But that means we have to have lots of reabsorption happening, because there's no way you could ever sustain making 180 liters of urine a day. You just don't have that much fluid. So we have that reabsorption. So making urine happens really in 3 processes. You have glomerular filtration, that we have to filter the blood to make the filtrate. We'll talk a little bit more about things that are happening in there. We have tubular reabsorption, the fact that 99%, 180 down to 1.5, 99% of that filtrate gets reabsorbed back into the from the tubes. And then we also have some tubular secretion, the fact that we can secrete things from our blood vessel into the urine to get urinated out. And I'm like, that's your 3 basic processes. I guess I have that written out here on this one. So filtration, you're making filtrate, but that filtrate is cell-free and protein-free. And I'm like, it's a filtrate. Lots of stuff comes out of the blood plasma, but cells are too big. And I'm like, and proteins are too big, that they stay in your blood supply and don't end up in your filtrate. Reabsorption is, again, we reabsorb 99% of the substances, and tubular secretion is anything going from blood into the filtrate to become part of your urine. So just kind of looking, because a lot of people get reabsorption and secretion switched around on what's happening. So filtration, glomerular filtration, we're going to filter the blood in the glomerulus, and that's going to become filtrate. So blood goes in, gets filtered, blood goes out, but it's filtrate that's made. 180 liters of filtrate are made a day. From all that 180 liters of filtrate that are made, 99% of it gets reabsorbed back into your blood supply, into one of those little peritubular capillaries. But we do have some stuff that's in our blood that we want to get rid of out of the body, and that can be secreted from our blood supply into the tubes to eventually end up as part of our urine. Now, we're going to talk in this intro video about the filtration. I will review a little bit in lecture, in class, but I'm going to start talking about the filtration process. Now, the filtration process itself is a passive process, which means we don't have to put any ATP into the process at all. The main pressure that causes filtration to happen is hydrostatic pressure. This is really, we're talking blood pressure. Your blood pressure, that pressure alone forces fluids and solutes, things that are dissolved in solution, through the filtration membrane. Now, the filtration membrane, again, its job is so that we can filter things. So it's a porous membrane. And the pores, more official term is fenestration. It's fenestrated. It's porous. It's a porous membrane. And so that we can have small molecules, anything smaller than proteins found in plasma, that can go through. So water can go through, small solutes can go through, cells should not be able to go through. Those are too large and they would get stuck in those holes or pores that are found in that filtration membrane. So I'm like, our job, it's all in these, is in this glomerulus. That blood supply has to go through that filtration membrane so that the smallest stuff can go through and become filtrate. And they even make it nice and yellow like urine, but filtrate is not technically urine yet, because again, we make 180 liters of filtrate, but only 1.5 liters becomes actual urine. So we got a lot of stuff to do this filtrate, but we filtered our blood, specifically the plasma portion of our blood. Now, it does happen that occasionally things get stuck in the filtration membrane, in those pores. We have cells that are located there that can engulf them. They can get rid of them. They're kind of just cleaner upper cells found around there. But generally, any molecule smaller than 3 nanometers can get through those pores. That includes water, that includes glucose, that includes amino acids, any nitrogenous waste. Big thing that doesn't make it through, other than cells, plasma proteins don't make it through. Proteins found in your plasma have to stay in your blood itself. That helps maintain what's known as our colloid osmotic pressure. Now, your colloid osmotic pressure is the fact, and it goes back to water follows solutes. Plasma proteins are solutes. We need to maintain that protein in our blood, because if the protein is there, the water stays with it. Water wants to follow solutes, and proteins are solutes. If we lost all of our proteins into the filtrate, so much additional water would become filtrate. Like, we would have too much and too fast of water loss. And so the fact that proteins stay in our blood itself maintains what's known as this osmotic pressure. Because when we're talking about osmosis, we're talking water moving. This prevents all of the loss of your water into that filtration membrane, or past that filtration membrane into the Bowman's capsule space. So if there are proteins that have made it into your filtrate, there's something going on. And I'm like, it's an issue. Your filtration membrane's damaged, your blood pressure is too high that it might be even pushing proteins through. Your blood pressure is so high. We do not want proteins in urine. It's an indication something's going on and it's never good. And so that proteins from our plasma need to stay in our blood supply, because wherever the proteins are, so is the water, and that keeps our normal blood pressure up. Now, pressures that affect filtration. It's all pressure. Again, it's a passive process. Well, there's one big outward pressure. This is the pressure that promotes filtrate formation, the fact that we can filter our blood plasma. And the big pressure that promotes filtrate formation is hydrostatic pressure in your glomerular capillaries. This is the blood pressure found in the glomerulus. This is a key thing, highlight it, star it, whatever. This is the pressure that promotes you to be able to filter your blood and make urine. Blood pressure. Blood pressure allows you to make urine, which means if your blood pressure is too low, you're not going to make as much urine. If your blood pressure goes up, you can make additional urine. However, if your blood pressure goes up too much, that pressure could damage the filtration membrane. But hydrostatic pressure in your glomerular capillaries just means your glomerular blood pressure, this is the chief force that pushes water and pushes solutes out of the blood and across that filtration membrane. Now, your blood pressure in these capillaries, in the glomerulus, is about 55 millimeters of mercury. That's high, because blood pressure in most capillary beds is about half that, because it's slow for oxygen-carbon dioxide exchange. This has to be high. We need that high blood pressure to push water, push solutes out of blood. And part of the reason why it's so big is because that afferent arteriole, the exiting arteriole, is smaller in diameter than the afferent. So you kind of have that extra pressure when you change the diameter to something smaller. Now, there are two pressures that slow or inhibit filtrate formation. The first one is hydrostatic pressure in the capsule space. So around the glomerulus, you have that Bowman's capsule or glomerular capsule, that space around there. Well, there's some fluid in there already. So you're not pushing fluid into an area where there's no fluid. And so because there's already some fluid, there's already some filtrate in there, and I'm like, that's going to slow down more filtrate going in there. And so it's just another pressure that's pushing backward on that glomerulus. And the pressure that pushes backward, because there's already filtrate in there, is about 15 millimeters mercury. You also have what's known as the colloid osmotic pressure, the fact that you kept the proteins in your blood. And because you kept the proteins in your blood, you kept the water in your blood. That means, and I'm like, if the proteins aren't going through, not as much water is going to go through. And because of that, it inhibits filtration from happening. So we want to maintain the proteins in our blood. And I'm like, it's going to slow down how much fluid can get turned into filtrate. And so that pressure alone, holding on to the fluid because of the protein, is around 30 millimeters of mercury. And so when we look at the force that pushes fluid through, and then we look at these two forces that inhibit moving of fluid through that filtration membrane, the sum of the forces is what's known as your net filtration pressure. Now, just looking at numbers, we have a pressure in your blood supply of around 55 millimeters of mercury. That's the blood pressure causing filtrate to get formed. However, when you add 15 and 30, you have 45. So you have 45 millimeters of mercury pressure opposing the making of filtrate. However, our blood pressure, or our pressure, our net filtration pressure, is a positive number. It's 10. And as long as that is a positive number, filtrate will get made. It means your blood pressure is higher than the pressures opposing it, which means you're going to make more filtrate. You're going to make more urine. Now, net filtration pressure. This is, really based on blood pressure. That's the biggest one. But as long as it's positive, you're going to make urine. But that's your net filtration pressure. Now, your net filtration pressure is around 10, give or take, responsible for making filtrate. And it is the main factor that determines your glomerular filtration rate. How much urine or how much filtrate can you make? And I'm like, is mostly, it's not only, but it's the main thing that determines how much filtrate you can make. This is just showing you the numbers. And I'm like, your glomerular capillaries hydrostatic pressure, aka blood pressure in your capillaries, is 55 millimeters of mercury. The two things that are opposing that is the fact that you already have fluid in this space, and the fact that you have the pull of the proteins and water with it opposing the making of it. As long as your 55 is greater than these two opposing, which it is, as 10, you're going to make urine. Now, your glomerular filtration rate, mostly controlled by that pressure of around 10, but it's not only dependent on that. And so the volume of filtrate that's made in your kidneys is you make about 120-ish millimeters of filtrate every minute. That's your normal filtration rate. Now, it's mostly dependent on that net filtration pressure, your blood pressure, but it's also dependent on what is the surface area available for filtration. If you have a larger surface area in your glomerulus, you're going to have more filtrate made. What is also the filtration permeability? Some of your some of those glomeruli are going to have more pores, and I'm like, well, it's going to be more permeable, and so you can have more filtration made, more filtrate made as well. Most of it's dependent on your filtration pressure. Now, I'm going to review some of this in class, but I at least wanted to kind of go over some of these basics first. One is, your glomerular filtration rate. How much filtrate can you make a minute? Allows your kidneys to make filtrate and maintain extracellular homeostasis, meaning your making of urine helps maintain our bodies. It maintains blood pressure, it maintains blood body pH, and it regulates a lot of our body. Now, it kind of has two goals for filtering. One, the intrinsic goals of your kidneys is to maintain your glomerular filtration rate. And as long as your mean arterial pressure, as long as your blood pressure is in the range of 80 to 180, kind of normal blood pressure, our kidney can maintain its glomerular filtration rate so that we can filter things out of the body. We can get rid of things out of the body. We can, I'm like, that's its main goal. We just want to get rid of things out of the body, whether it's because we filtered them out, whether it's because we secreted them out and it leaves. But we want to maintain a constant glomerular filtration rate. That's an intrinsic control. It's kind of an internal control of our urinary system. Now that's if it's between 80 and 180 degree, or 180 millimeters mercury blood pressure. But our filtration rate can also affect our systemic blood pressure. That's an extrinsic control. So the fact that our urinary system is going to not just maintain our urine of what's in our urinary system controls our blood pressure. It's sad to say, your urinary system controls your blood pressure. And so there is an extrinsic control of your urinary system. That's to maintain your systemic blood pressure. If your glomerular filtration rate goes up, and I'm like, that's going to increase urine output, which means you're going to have blood volume go down. And I'm like, when blood volume goes down, blood pressure goes down, and vice versa. And so if your blood pressure is rising, your blood pressure is rising, you're going to increase urine output, and you're going to bring that blood pressure right back down. It's the same basic idea. If you just drank a big liter of water, you just gulp down a liter of water, your blood volume goes up because you now have a liter of water in your body. Your blood volume goes up. When volume goes up, pressure goes up. And so you drank a liter of water, your blood pressure went up, not a ton. We're not talking that drinking water is going to create blood pressure issues, but it could rise, a couple millimeters of mercury. It's going to increase urine output. And I'm like, you're going to urinate, and it will bring your blood pressure right back down to normal resting blood pressure, and vice versa. And I'm like, your urinary system controls your blood pressure, and a lot of this because it's controlling blood volume. Now, your nervous system and endocrine system also can maintain blood pressure. We're not talking that the urinary system is the only thing that's maintaining blood pressure. And I'm like, it does have an effect on your blood pressure. Now, unfortunately, if you were starting to change urine output to change blood pressures, and even blood pressures being regulated by other systems, your kidneys can get damaged by blood pressure issue. Now, generally your extrinsic controls are going to take precedence over intrinsic control if your blood pressure is less than 80 or more than 180, meaning outside of normal ranges. And I'm like that if your blood pressure is out of range, we don't really care about making urine anymore. Our main goal in life is survival, and our precedence is going to try to get that blood pressure back into range. And so if your blood pressure is out of range, urinary system's going to take over. It will stop making urine. Maybe it will make too much urine, but it really doesn't care about making urine anymore because it needs to get your blood pressure back into range. Now, if your extracellular fluid volume gets extremely low, meaning you had severe hemorrhaging after surgery, something, if your blood volume gets extremely low, your blood pressure is also going to be extremely low. This is, now we're going to get into, it's an extrinsic control. You're going to be outside of normal ranges, and your sympathetic nervous system is going to take over. And I'm like, again, blood volume getting too low, blood pressure getting too low can be deadly. Going to try not to die. And so your sympathetic nervous system is going to take over. It's going to cause norepinephrine to be released, which is going to cause epinephrine to be released by your adrenal medulla. This is going to cause vasoconstriction of various blood vessels. And it's normally going to be blood vessels in your body. And I'm like, and when you constrict blood vessels, that can increase blood pressure. Because right now your blood pressure is really low. So we can constrict various types of blood vessels, not all of them, but we can constrict blood vessels to increase blood pressure. We can also constrict your arterioles around your afferent blood vessels. These are the ones that are normally wide and then get narrow as they're efferent. Well, we can constrict your afferent blood vessels. And when you constrict those afferent blood vessels, you're going to have less blood going into your glomerulus. You're going to have less filtration happening. You're going to have less filtrate getting made. Pretty much you're going to stop making urine. You don't want to. If your blood volume is extremely low, the last thing that your body wants to do is make urine. And so we want to maintain and keep that blood plasma there. We want to stop making or slow down making filtrate. And this will help increase your blood volume. And if you increase blood volume, you also increase pressure. And so your urinary system is very much affecting your blood pressure. Now, there are some hormones that can also increase blood pressure, and these can have an effect on your kidneys. It's renin. We'll talk a little bit about renin, angiotensin, and aldosterone. And aldosterone is one hormone that we'll talk about in our next section. But I'll review some of this in class, but I at least wanted to kind of give you some basic idea with the filtration happening in there and how important the filtration is and how filtration can affect your blood pressure. Now, some of the review at the end. Urine collection occurs in the what part of the kidneys? And so we're talking collection, and we're talking the part in the kidneys, and the part that collects urine in the kidneys is the pelvis. And so it's collecting from all your minor and major calyces, and it's all collecting in the kidneys in that renal pelvis. Then it leaves through the ureters. The blood filtering structure of the kidney, and it's the filtering, and filtration happens in the glomerulus, that capillary right there. The urine-forming units of the kidney, nephrons. It's the nephrons that make the urine. The vasa recta, which are capillaries, are associated with which structures in the kidneys? And that's the juxtamedullary nephrons. That vasa recta is the capillaries that surround that really long nephron loop. Which of the following factors contributes to the high filtration rate in the glomerular capillaries compared to other capillary beds? So what has, well, I don't want to say it, but what allows that high filtration rate to happen in the glomerular capillaries? Well, it's all of them. It's the fact that your capillaries are porous. The diameter of the efferent that leaves is smaller than the diameter of the afferent, the one that goes in, and that the glomerular capsule as well is also porous. So we've got lots of things that have holes. We have a nice high blood pressure, all contribute to high filtration rate. Your extrinsic controls regulate your glomerular filtration rate as a means of regulating blood pressure. So your urinary system controls your blood pressure, and we're going to end right there.